and welcome everyone to the dam removal virtual short course. As you mentioned, I'm Courtney Chambers from the ERDIC Environmental Laboratory, and I'm glad you're here today. This short course is brought to you by the Ecosystem Management and Restoration Research Program. And throughout the course, we've been learning to characterize and evaluate potential impacts from release of sediment associated with dam decommissioning. We've learned to develop an approach for screening sediment issues, and then to use tools for assessing sediment impacts and benefits. Today, we're going to continue with a focus on modeling techniques. Part 4 is going to provide an overview on how one-dimensional and multi-dimensional modeling can be applied to predict sediment transport and potential impacts associated with dam removal. Case studies with applications of these modeling techniques are going to be presented, and this will include an application of the 1D HEC-RAS model to the removal of Simkins Dam on the Patapsco River in Connecticut, and the use of the GSBM to evaluate sediment transport following Milltown Dam removal in Montana. So as you likely know by now, this will be the last session of a four-part course that we've been working our way through. Other sessions have been archived online at the Ecosystem Management and Restoration Research Program website under the Webinar tab, and I've provided that link here on the screen, but we'll also copy that into the chat feature so that you can quickly visit that page. We are breaking each course into a Part A and a Part B, and you can access the bios for each speaker as well as the PDF of the slides presented, and then also the video as it's available. So as of today, Class Session 1, Session 2, and part of Session 3 are posted, and the additional videos will be made available soon, shortly. And you'll be notified by email once all of those files are available, and then you can go back to visit at another time or share with colleagues who are unable to attend a live session. I did want to mention that a PDH credit is available for attending the short course. So if you're interested in receiving 1 PDH for each short course session you attend, please send me a message. I am tracking those as we work our way through the course, and once we complete our session today, I will send those certificates out in the next week. All right, our agenda for today's session, as we've done in our prior meetings, we're going to have a Part A and a Part B. Part A will focus on the one-dimensional numerical modeling applications and the Simkins Dam case study. This will be presented by Ms. Valeska Echeverria-Doyle. And then we'll have questions from her presentation, and then we'll take a short break with an optional activity, and then we'll start into Part B. And that's going to be a Milltown Dam case study, and it will be presented by Dr. Earl Hager. So that's what you can expect from the day. After Dr. Hader's presentation, we'll again take questions and answers in discussion, and then we'll wrap up our meeting. So that's the plan for the day. Without further delay, let me introduce our first speaker. Ms. Valeska Echeverria-Doyle is a research hydraulic engineer for the U.S. Army Engineer Research and Development Center in the Coastal and Hydraulics Laboratory. Prior to working for the ERDIC Coastal Hydraulics Laboratory, Valeska worked as a hydraulic engineer with the U.S. Army Corps of Engineers at the Buffalo District from 2010 to 2014. While working for the Buffalo District and CHL, she has worked on numerous projects and research studies related to flood risk management, hydrology, and sedimentation. She holds a bachelor's in civil engineering from the University of Puerto Rico and a master's in civil engineering from the University of Illinois at Urbana-Champaign. She is registered as a professional engineer in the state of New York. All right, Valeska, at this time we'll transition to your slides, and you can begin.
Okay. Thank you, Courtney. Good afternoon. Thank you for attending the last dam removal webinar series today. I will be talking about one numerical model application that could be used for dam removal, and I will be also discussing some of these applications, how you can use them, and the Simkins Dam case study was the one I used to prove some of these applications. All right. So first, I would like to briefly talk about some concepts that have already been discussed in previous webinars. One of those concepts is the sediment behind the dam a concern? This is one of the questions that are typical when a dam is considered to be removed. And some cases, the sediment might not be a concern. It might be considered negligible. And if that's the case, usually a sediment analysis might not be required. So from the dam removal analysis guidance for sediment, there are very useful information that could assist with determining if that sediment behind your dam might be considered negligible or not. But if it's not negligible, then what we need to then ask, what are then the concerns I should be paying attention to? All right. So from the it's a very good journal article published by Toulouse et al. In 2016, there's a list of common management concerns that have been identified for dam removal cases. From those concerns, there are 4 that are directly related to sediment, and have them right here. Degree and rate of reservoir sediment erosion, excessive channel incision upstream of the reservoir, downstream sediment aggregation, and elevated turbidity. So part of the case study that I will be discussing with you today, I'm using these 4 common management concerns as a guide to identify outputs from a 1D numerical model that could potentially inform these concerns. Last webinar, Dr. Lackey provided very good information about a list of different tools or methods that could be used to quantify the geomorphic implications of dam removal. And today I'll be focusing on specifically on 1D sediment transfer modeling. Before I start talking about sediment, I just want to bring up some basic concepts about the equations of water motion in one-dimensional form. It is assumed that forces acting on the body of water are predominant along the river's center line, and vertical or lateral forces on the body of water are considered negligible. This is an assumption that is used for 1D modeling, and it's sometimes in the real world, we know the real world is more complex than this, but there could be situations where you could make this assumption and still get utilize a 1D tool that can still give you some results that are fairly reasonable comparing to what happens in the real world. There are also cases where this assumption is no longer applicable. Maybe your system is more complex, maybe the vertical lateral forces are not negligible, and you might need to consider a more complex numerical model to look into your system. I just want to bring up, if any of you are interested in knowing more about differences between one-dimensional models versus two-dimensional models or three-dimensional models, there's a training document that was recently published by the Hydrologic Engineering Center in collaboration with the Coastal Hydraulics Lab. And it's a fairly useful document that provides some very good information that might help you identify when one model might be better than the other. And also they talk about steady flow versus unsteady, which is another frequent question that hydraulic modelers can have. And why hydraulics are important? Because hydraulic input is required for sediment transfer models. So when you're doing 1D sediment transfer modeling, the input that you're getting, the hydraulic input you're getting, it's based on those assumptions that I just mentioned. All right, so today I'll be talking about 1D numerical sediment transport modeling, specifically the HEC-RAS model, version 5.0.7. And some of the capabilities that this model offers is to route sediment and adjust cross-section, aggregation or degradation patterns along the ridge of interest. What I mean with aggregation is when there's a deposit of sediment at certain location. And degradation means when I'm losing material, there's erosion occurring at certain locations. So basically, this model can adjust the initial bed conditions based on sediment dynamics and hydraulic inputs. Some of the model outputs that could be used to inform common management concerns related to sediment are the profile elevation change. So basically what that means is when you have a hydraulic model, a 1D HEC-RAS hydraulic model, you need to define your geometry. And when you only do hydraulics, that profile is going to be fixed. It's not going to change no matter what flow you're running through the model. But when you do have a sediment model, that initial profile is going to adjust over time based on hydraulic inputs and sediment dynamics. The model can also provide some volume calculations, so you can kind of look at specific parts of your system and see how volume has changed. Have you gained volume? If there has been some erosion, how much volume was lost, things like that. And this model can also predict sediment concentration. So today I'll be talking about the Simkins Dam case study. Here I'm showing three pictures of the site. The upper left, it's when the dam was still in place. The bottom center picture shows when the dam was being removed, and the upper right picture is what it's now. It's basically the entire dam was removed, and it's a free-flowing river at that location. So the study reach, it's located in the along the Pataska River, and it's about southwest from Baltimore, Maryland. As you can see in the figure, there's a black square rectangle. That is pretty much the area, the study area that I use for the model. The Pataska River watershed area is about 367 square miles. The study reach is about 8 miles long. The reach is located within two different regions that are geologically different. So most of our study reach is located within the Maryland Piedmont, which it has gravel-bedded characteristics. It has steep slopes, and it also, there's some sections of that part of the reach that are fairly narrow. And right at the fault line, that's also shown on the picture, in the lower parts of the study reach, it's within the Atlantic coastal plain. That part of the reach is fairly different to the Maryland Piedmont because it's sand-bedded and the gradients are lower. There's the Bloody Dam that is located about 3,000 feet downstream of Simkins Dam. My understanding is like this dam is either in process of being removed or it has been removed already, but by the time the Simkins Dam was removed, Bloody Dam was in place. Hydrology of our system, we have a base flow of about 67 CFS, mean annual discharge of 265 CFS, and mean annual flow of 14,000 CFS. So the dam description, it was about 10 feet tall, 217 feet wide. The operation was run-of-river. Construction was in 1889. It is considered a full removal because the entire structure was removed. The removal took place in the fall of 2010, and the purpose of removal was to improve public safety, aquatic habitat, and migratory fish passage. It was a mechanical removal, and the stored sediment texture is dominantly sand with some gravel. At the site, there's lots of data that were collected prior to the removal of the dam. The first survey was in September of 2010, and that was a pre-removal survey. The surveys included channel geometry information. There were like total of 28 cross-sections that were defined along the study reach, 5 monitoring areas. The survey also included the material information, grain size distribution, to gradations of pebble count, plastic map, full density in both Simkins and bloody stored deposits. The following surveys, there's a total of 6 surveys that took place after the dam was removed. And the same information was collected at the same location for all the following surveys. And this data provided good information to have an understanding on how the study reacted to the removal of this dam, where the sediment went, how my bed elevation changed along the ridge, et cetera. There are also 3 gauges, USGS gauges. One is located at Holyfield, Maryland, which is upstream of the study reach. And the USGS gauge located at Campbellsville, Maryland is right downstream the Simkins Dam, the former Simkins Dam location. And the Elk Ridge USGS gauge is located farther downstream in the reach, downstream Simkins and Bloody Dam. All of these gauges have water discharge, water stage information, water temperature, sediment discharge, suspended sediment concentrations, and water quality samples. So as you can see, this site has lots of data, and especially after the dam was removed, which is data that could be used to verify tools, like the one I'm going to present to you today, to look at tools and see how these tools could predict changes that occur after the dam is removed. So for the sediment transfer model in HECRAS, so like any other tool, you need some data to be able to build a model. The most important data for this type of model is that you need cross-sections of the altimeter. You need to know how your reach look like, your cross-sections, and typically the geometry file that you use in the sediment transport model is basically the same file you use for the hydraulics. So basically that geometry file includes cross-section data, but it also includes other parameters that are required for hydraulic analysis, such as roughness, bank delineation, ineffective fault areas, etc. For the sediment data file in the HECRAS model, you need bed material gradation. So you need to define your gradations at every cross-section along your reach. You also need to know some information about like incoming sediment load, what's coming into your system. That's usually typically used to define your upstream boundary sediment condition. in the model. And it will be ideal if there's any bedrock location that you know of through data collection or geologic maps. This is important because you could set up the model to limit erosion. If you had erosion, but you know that there's bedrock at certain elevation, you could specify that in the model so that the model does not predict unrealistic erosion at locations where it's known that there's bedrock. And that data goes into the sediment data file, and the sediment data file also has parameters. There's certain equations that you can pick to do your sediment analysis. But having that data can help you make certain decisions to have your sediment data file set up. You also need your discharge. You need some sort of a hydrograph that you're going to use for your study, and you also need water temperature to complete your flow file. All right. Well, what did I find from this Hecker's model looking at data I was collecting in Simkins? So basically, I developed a hydraulic model for Simkins for the REACH study, and I also built this sediment transfer model. And because the site has data that was collected after the dam was removed, I was able to compare how the model was able to predict erosion and deposition along the reach. So the picture that you're seeing here, the first one on top, represents the profile elevation. The name of this output in ECRA is the mean effective invert elevation, which means it's the average elevation across your cross-section. And the black dotted line represents my initial profile. That's what it was right when the dam was removed. But throughout time, part of that sediment that was behind Simkins eroded downstream. And we can see in the blue continuous line on the first picture on top, you can see that the model predicted that the bed was going to degrade at that location. And when I compare what the model predicted to the blue dots, which are the locations where cross-sections were collected in the field, the model was able to fairly good, did a fairly good prediction on like how that new profile was going to look like. And something important to notice here is that for the February 2011 survey, which is the one represented by the blue continuous line in my profile figure, I am pointing out to this cross-section figure here, and then you can see at that location that I selected, which is right downstream the dam, you can see my initial profile, which is, again, the black dotted line. Then you can see the continuous blue line, which represents what the model estimated, and the blue dotted line is what the observed cross-section was at that time. So it tells me that soon after the dam was removed, immediately downstream the dam, there's some deposition occurred. And the model was able to peak on that, and it was fairly close to what was observed. Farther upstream in the Simkins reservoir, the orange continuous line represents how the profile looked like by November 2013, which was the last survey. And then the orange dots represent locations where cross-sections were collected. And again, the cross-section farther upstream here with the orange line, it represents also comparing the initial profile with how the profile changed by the survey of November 2013 and comparing that to what was collected at the field. An important thing to notice also, by November 2013, that initial aggregation that occurs right downstream the dam, that sediment continued to move downstream. So in that location, the profile went back to close to what it was initially. How can this inform common management concerns? So the degree and rate of reservoir erosion. For this particular case study, a large amount of sediment mobilized from the reservoir by the February 2011 survey. And then it continued to erode, but a lot less material. So that's something the model could pick up on. Also, the excessive channel incision upstream of reservoirs, you can see the initial profile, how it changed over time, and how that it degraded farther upstream. It also showed that there was a temporary sediment aggregation that occurred immediately downstream the dam. But then we learned after looking at the 2013 data that deposition that occurred immediately downstream, it didn't last forever. It just that sediment continued to move downstream. Something else that we looked from the model was the volume change. So I was able to look at how much volume was eroded from the sediment from the time the dam was removed to the survey of November 2013. From a study that Cooley et al. 2019 published, they estimated that from removal to the survey of November 2013, about 56,350 cubic meters of sediment were eroded from the reservoir. And the model was able to estimate a volume that was less than 10% difference to what Q published. So that tells me the model was also able to estimate a reasonable volume of eroded sediment. We also looked at sediment concentrations. The model was able to pick on the increase in sediment concentration. So there's an increase in the sediment concentrations, but then when I compared that data to the observed data at the Cantonville gauge, which is right downstream the Simkins dam, the model overestimated mostly those sediment concentrations. As part of this study, we also wanted to do some sensitivity analysis because we want to have a better understanding on, like, okay, so you have your data, put your model together, you calibrate your model, but then what is the model sensitive to? What are the inputs that I can put in my model that can dramatically change my results? And if any of you have done sediment modeling before, it's a highly sensitive modeling. So sometimes we change certain things in the model and can make a big difference. Here I'm providing a definition of a sensitivity analysis, which is commonly used to examine how the model output deviates from model calibration results because of variation of input factors. So for the sensitivity analysis for Simkins, I selected some input data and some model structure, and I tested that to see how much of a difference I can see in the results. For the data inputs, I basically I picked the sediment gradation specifically along the Simkins reservoir, and what I did was I used the gradation I used for calibration. I made that finer, maybe around 20% finer. Excuse me. And I also got that same gradation, and I got a slightly coarser gradation, about 20% coarser gradation. And then I run the model, just changing that. The rest of the parameters and everything will be the same as a calibration. And with that exercise, I could see how that would change my results, just by changing gradation. I also looked at model structure. For the HECRA sediment model, you need to specify your sediment transfer function, and that's basically an equation that predicts rates of sediment transport from given hydraulics parameters and sediment properties. In our case study, we are dealing with non-cohesive sand and gravel. So I picked sediment transfer functions that were developed for that kind of sediment because there are options in the model, but not all of them were designed for sand and gravel. So you need to make sure you pick the ones that are developed for the right sediment you have in your system. And in this case, I use YAM, the transfer function YAM for calibration, and I compared that with Akers-White and Mayer-Mueller. I also look at the sorting method. The sorting method is an algorithm that mixes the bed. So basically, you have your initial gradation, but that gradation will change over time based on how sediment dynamics and how this algorithm kind of makes up the sediment coming through the system. I use active layer for calibration, but then I compare that to another method, which is called XNS5. And last, I also look at erosion for sediment deposits. HECRA offers like the veneer method, which is the default option to change cross sections in HECRA. And basically, for that option, you define your movable limits. You define what part of your cross section is going to move. It's going to erode or experience degradation or aggradation. I use that model for calibration, and I compared that with the channel evolution model, typically called Cantelli algorithm. So basically, that algorithm, you can estimate how your incision channel might look like, and you basically provide to the model some dimensions for a trapezoidal channel. You have to include your width and your side slope. And for this sensitivity analysis, I pick a width of 80 feet and a slope of 0.5 feet over feet based on cross sections farther upstream from the reservoir that were not impacted by the reservoir. So I kind of assumed that the incision channel was going to look similar to the cross sections farther upstream. So here is a plot where I'm showing how my profile elevation compares to calibration values when I change the inputs that I just described. And the profile elevation is highly sensitive to the sorting method. Just changing the sorting method to XNR5, it produced a way deeper profile when I compare the elevations that were estimated for the calibration result. A finer gradation will also generate a deeper incision channel, so my profile elevation will be a lot deeper. Following the erosion method, and as you can see, the transfer functions made a difference in the results, but they were less than sorting or depth material gradation. That tells me that even if I'm using transfer functions that are not exactly the same, the fact that they were designed for sand and gravel materials, the model wasn't as sensitive as it was to bed material gradations and sorting methods. I also look at the volume that eroded from the reservoir from removal to November 2013. And I was able to identify that, again, model was fairly sensitive to finer gradation, produced a lot more volume than the volume that was estimated by the calibrated model, following by the sorting method, which also produced a lot more volume than what it was predicted for calibration. And so it is interesting to notice here that Cantelli, the parameters that I used for the sensitivity when you compare that Cantelli cross-section with the actual cross-section I use for calibration, the Cantelli is slightly smaller. The area is slightly smaller, so it produced a deeper channel, but it didn't produce the volume was fairly close. I'm guessing because the calibration cross-section was slightly wider, so it had a little bit more dead bottom to erode from. So that was an interesting finding. So what did we learn from this? I guess 1D models could inform common management concerns. For the Simkins study, I applied a 1D model because, as I explained earlier, most of the study reach that was used for the study was within that Maryland Piedmont region, which is usually, steep and some narrow areas. So that 1D assumption that the water motion of the force of water would be in one direction is fairly something that in this region could be applicable. And so I learned that with the 1D model, I was able to see how my profile elevation changed over time. I was able to see areas downstream that experienced aggradation, and then throughout time, so that aggradation in this particular case was temporary. And I was able to see how the incision channel progressed upstream, just comparing model results with observed data. The sediment concentrations, the model over-predicted some of the sediment concentrations based on observed data, but I think it's still good to know that this model can predict this. And again, this is results for just one case study. It doesn't mean the model won't be able to predict this correctly for other case studies. So it's important to know that this is an option that we have as well. And then from the sensitivity analysis, so we know that the model for this specific case study, the model was highly sensitive to wet material gradation and sorting methods. I just want to emphasize that in hydraulic and sediment modeling, our site can be very different. So the fact that this specific case study was highly sensitive to these two inputs doesn't mean every model will. Certainly, degradation won't make any model sensitive to, because that's pretty much what the model uses to route sediment, and the sorting will be the way the model adjusts degradation. So you could expect other cases to be sensitive to that as well, but I just want to just want to emphasize that these are results from Simkins specifically. Also, for the sensitivity to the channel evolution model, Cantelli, I used some parameters for this, but if you use something different, like if you assume your cross section will be a little bit wider or your side slope will be a little bit different, I would expect the model will show some sort of a sensitivity to that as well. And the model showed less sensitivity to transfer function, and my assumption to that might be because the transfer functions that I use, all of them were kind of developed to deal with non-cohesive sand and gravel material. I would like to say thank you to Mr. Matt Collins from NOAA. He provided gradations and cross-section data from all the surveys that I mentioned earlier in the presentation. I would like to also thank Dr. McKay and Susan Bailey. They have been involved in the design of our study, and we have shared fairly good information and feedback throughout the process. So I want to say thank you to all of you. And if you have any questions, please type your questions in the chat box, and I'll be glad to answer. Thank you, Alaska. Go right ahead. Sorry.
Ladies and gentlemen, if you would like to submit a question in a written format, please be sure to select all panelists from the drop-down menu in WebEx chat before you type in your question and press enter on your keyboard. If you would like to ask a question on the audio line, please press #2 on your telephone keypad. When your line is unmuted, please state your name and question. Once again, that phone command is #2 for audio questions. Thank you.
All right. Thank you, Alaska, for your presentation. We haven't received any chat questions just yet, but please do type those in and send your question to all panelists so that our speakers will be able to view those. And we'll give a few minutes to get those in. I'm also going to go ahead and share the link to the course files that you can access and see what we've covered thus far in the course, as well as save that link for the recording of today's session.
We do have a question on the audio line.
Okay,
caller, your line is unmuted. Caller, please go ahead.
Yes, my name is Dan Ridgely from the Baltimore district. Just a quick question. I know you said this was done as a 1D. Have you done any 2D or as a comparison to see how they behave or the differences? Over.
Thank you for your question. Yes, that's a very good question, and that's something we as a team have thought. We do not have a 2D version of this model. We only have 1D for now, but it could be a good project for the future to compare how 2D will do and compare, what the 1D versus 2D model can offer.
Thank you.
Okay, there are no further questions on the audio line at this time.
Okay. We did get one in the chat feature. Waleska, how far downstream did your model look?
I didn't show the entire reach because it will be kind of hard to see the results. I kind of zoom in into the reservoir area and farther and immediately downstream, but it's about a mile long.
How many did you say?
Excuse me?
I'm sorry, how many miles did you say?
It's about 8 miles long.
8, okay.
Forgot exactly how many miles upstream the Cheeky Bay. I can go back to the site. So I'm just going back to my site description slide, and in this dark black rectangle, that's where the study reach is. So it's a lot longer than what I showed on the presentation. It's just that I kind of wanted to zoom in into the area closer to the dam. But yeah, that's pretty much, it's about 8 miles long, and I forget exactly how far from the Cheeky Bay was. And that's, looking at the picture, maybe you can have an idea.
Thank you, Alaska. Event producer, do you have any other phone questions?
There are no further questions at this time.
All right, well, we'll pause another minute or two. All right, another one, Waleska. Did your model assume the presence of blowed dam? I don't know if I'm pronouncing that correctly.
Yes, I did assume the presence of bloated dam because the dam was in place prior to the Simkins removal, and even after the dam was removed, the bloated was still in place.
So has that been removed since that time? Or can you give some further context to that?
So because the dam, during the time frame of my study, Bloody Dam was present, so it was part of the model. Yes, it was included as part of my 8-mile reach.
Okay, thank you. I guess my question was, has it been removed since your study?
Oh, I'm sorry. Can you repeat that again?
Has it, I guess I was wondering then, does that mean the Bloody Dam has been removed since that time?
Oh, I'm not sure. My understanding is that dam was scheduled to be removed, but I'm not sure if it has already been removed or it's still in plan. Oh, okay. Someone just said that it was removed. Do you know when was removed, Andy? Okay. Well, we're fairly recently then.
All right, and just since our attendees can't see all of the chat coming to the panelists, our participants shared that it was moved in 2018 and that we can watch those videos on the Maryland Department of Natural Resources website.
Okay.
Thanks for sharing, everyone. All right, any other questions for Waleska before we take a break?
There are no further questions in the queue at this time.
All right. Well, we don't want to rush anyone by any means, so please continue to send your questions in. We have plenty of time during our course today still to address them, but let's go ahead and pause for a brief break. We will take 10 minutes, and then we will begin Part B. So if you would, I've got a activity that you can participate in on your screen. You can utilize your annotation tool. Now, this is entirely optional, but after you take a break, if you want to turn on your annotation tool and highlight words in this word search, we can work together on it, and then I can show you the answers when we get started. But we'll pause for 10 minutes. Let's start back at 2 o'clock Central Time, and we'll get going with Part B from Dr. Earl Hader.